Today we're going to talk about speaker technology. The cone speaker, which you're very familiar with, has some inherent problems which we need to discuss. In the first slide, entitled Multiple Phase Emissions, we're talking about the shape of the cone speaker itself. To create sound, the entire cone moves forward and backwards. If we take a look at emitting the sound that we want, and look at a point on the cone. From here it moves a compression wave forwards as it moves. That's the sound that we want. However, the cone has some depth. So as we progress on to the second slide, we'll see that farther up on the cone it's farther forward, and depending upon the frequency you're trying to produce, that may be a quarter of a wavelength more advanced towards the front than what you were emitting here. So now you're emitting the sound that you want, and now you're emitting a quarter wavelength more advanced in phase at the center of the cone. And as you go to the third slide, now at the tip of the cone, that may be a half wavelength more advanced. So as the cone moves at the same time, you have multiple images of what you're trying to clearly communicate or clearly hear. The wavelength, a quarter wavelength more advanced, a half wavelength more advanced. And since all of these are coming out of the cone at the same time, they collide with each other right in front of the cone. They construct each other, they deconstruct each other, they interfere with each other, they create distortion, or what we're calling compression wave chaos. It's not what you want. Multiple copies laying on top of each other are destructive to hearing clearly what you want to hear, clearly reproducing what's in the original recording. This is what we call multiple phase emissions, collisions. Now that's only one way in which a cone speaker has problems having high fidelity. If we go to the next slide, it's called perpendicular wave collisions. Now in physics, when something moves and creates compression waves, it tends to emit those waves at a right angle to the surface moving. So even though the cone is moving in this direction, it's actually pushing compression waves off at a right angle to the surfaces. And since these surfaces are facing each other, what happens is the waves emitted from this side and this side, which is all what you want to hear, actually collide in the center of the cone. This is what we call perpendicular wave collisions. And as we go to the very next slide, this is something actually by manufacturers of cone speakers, and to quote them off of their literature, due to the shape of the conventional loudspeaker cone, the higher frequency sound waves tend to collide at a focal point. This causes phase distortion and a loss of clarity. As a result, accuracy and transparency suffer. This also has detrimental effects on the realism of the sound environments created by today's high-fidelity digital, audio, and surround sound systems. So this is acknowledged as part of the challenge of using technology that dates back to the 1930s. In the very next slide, there's a third way in which cone speakers distort sound, and this is called 10 cone distortion modes. Now what we mean by that is, as this cone moves, everything gets into vibrational modes in which they move and distort. You can think of it as if you just have a plane or a piece of paper, as they vibrate, not all of it moves at the same time. And here's where the problem comes. If you were a physicist and you were asked to come up with the ideal shape for something to make clear sound, you certainly wouldn't have picked a cone or a circular shape, because a circular shape gets into so many different modes of having waves within waves of pushing forward and pushing back at the same time on these different parts of the surface, that it creates many opportunities for distortion. So here's how the distortion happens. As a cone speaker moves and distorts along its walls, this part of the cone may be pushing the sound forward, which is what you want, creating the correct compression wave. But this part is actually pulling back. And so now you have what you want being pushed forward and the opposite copy of it being pulled back into the cone in the opposite direction. Again, these are out of phase with each other. They're in opposite directions. They collide, they deconstruct, they cause distortion, they cause compression wave chaos. Now we're going to show an animated physics study of this cone shape as it goes through different vibrational modes. And in this animation, what you will see is you have a primary mode where, the primary mode, which is the first one being shown, the speaker moves forwards and backwards all at the same time. That's what you want. But there's 10 other modes in which, now it shows the secondary mode, in which part of it's moving forward, part of it's moving back, half and half. The very next one down divides it up into 4. 2 at opposite corners are pushing up, 2 are pulling down. Again, it keeps getting more and more complex. In another mode, we even see where the center of the cone can be pushing in while the outer surface is pulling out. And we keep going through more and more complex combinations of just different parts of the surface moving forward and backward at the same time. You can see even in the next case, there's 8 sections of the cone which are all moving in different directions to each other. So it's truly a problem. In the very next slide, it shows all 3 of these different phenomena with a cone speaker. The multiple phase emissions at the top, where there's collisions in the air. The perpendicular wave collisions, where there's collisions right inside of the cone itself. And then finally, the 10 cone distortion modes. And now we're going to show a different approach. Not a cone speaker, but in fact a mad transducer. This is a very different type of technology to produce sound. But as you see in the first slide, it shows a single plane which moves back and forth to create the sound. So by design, it has just a single phase emission because all of the surface moves backwards and forwards at the same time. There are no surfaces that are in different dimensions to the front of surface. It's all at the same surface, and so you just have a single flat plane source moving. So that avoids the problem of multiple phase emissions. Secondarily, again, looking at where they had the problem with the cone, and you had collisions right inside of the cone itself, perpendicular wave collisions, there aren't any. You have a single flat surface moving, everything is moving at a right angle off the front of the surface. There's no surfaces facing each other to cause perpendicular wave collisions. Everything is radiating in plane. The third case, we show the plate actually going into distortion modes, and there's physics to that. However, we're going to show an animation which shows that instead of 10 destructive modes, there's only 3 destructive modes because by design, using a flat plane which is a rectangle only has 3 modes that are destructive. The significant difference is when the plane starts to get into a mode that can cause some of these problems, every square inch of the surface of this plane is covered with circuitry that interacts with a very strong magnetic field and electronically damps the plane from going into these parasitic modes. This is another advantage over cone speakers because cone speakers do not have anything like this that mechanically and by its intrinsic design keeps these parasitic modes from happening. So now if we go to the slide, the animated slide that show these modes, you'll see that in the very first mode, the primary mode is what you want. All of the plane is moving forwards and backwards at the same time. The next mode goes into front to back, where half of it's moving in, half of it's moving out, but this is damped in our case. The next is when they move side to side, and then finally in the last mode it's divided up into 4 pieces where 2 corners are going up while the opposite 2 corners are going down. So we have addressed making clear sound by changing the basic physics of what we're using to making sound with. So now, if you go to the next slide, entitled Mad Transducers, it shows single phase emissions, no multiple phase collisions, no perpendicular wave collisions, and the minor plate modes are damped. The end result is you have phase coherent projection of sound. What was recorded is what's being propagated through the air. Very next slide, we want to show another advantage of the transducer technology, and that is a mad transducer is 4 ohms resistive. In other words, no matter what frequency you're at, to the amplifier it's 4 ohms. That's not true with cone speakers. Cone speakers, the center of it is a coil, and a coil wrapped around a magnetic core. And as that moves, it has back EMF. Bottom line is that depending upon the frequency, the resistance varies all over the place. With a 4 ohm speaker being shown, the resistance varies up to 32 ohms from its base value. Our device, whether it's 20 hertz or 20 kilohertz, it's all 4 ohms. So now all of a sudden, a cone speaker is much more challenging to control with an amplifier because it creates a certain voltage. That's supposed to create a certain current, which is supposed to be a certain amount of energy to move the cone. If that varies depending upon the frequency, when you have multiple frequencies going through the cone at the same time, you have all kinds of problems just trying to control the output on that speaker. The next slide is called Wavefronts and a Conical Horn. And as you see, on a horn, you also have problems. If you could come up with a perfect planar sound source, no phase distortion at all at the mouth of the horn, if you could do that, then just progressing it through the horn, you'll see that it changes phase, it has phase collisions all through the mouth of the horn all through the horn itself, and by the time you get to the mouth, you again have chaos. So both technologies have inherent problems making distorted sound. The next slide, and this is a very important point, by the way. Right now, a lot of systems are being measured based upon SPL, sound pressure levels. Sound pressure levels is not a measurement of clarity. It's simply a measurement of how much energy is in the air. The energy in the air can be distortion, it can be chaotic sound, it can be a lot of things other than what you're really trying to hear. If you're really trying to hear sound, what a person is saying, then you have to hear everything that they're saying. Especially when you're trying to understand words, the difference between rent and cent and bent is what they call a soft consonant. It's what they call plosive, which is you're pushing air out of between your lips or your teeth. It's a T or it's a P. If that is lost in the chaos of collisions in the air, then you can't understand what the word is. human brain is the best digital signal processor around. And even though you may have 80 dB of SPL, energy in the air, there may be so much that the brain has to try to filter out to find the intelligent content there, the word it's trying to hear, that a much smaller signal, say 1/10 the amount of energy in the air that is clear, is easier for the human brain to understand than trying to find it in the middle of 80 dB of distortion. And that's what the next slide shows, is that in the middle of this distortion, the brain is trying to find just those parts which make sense and understand the word that's being said. So SPL is the wrong way in which to look at whether information is being communicated. The correct way is actually using the human brain, listening at a distance, listening to words that you can't imply should be there. If you listen to a string of words in a sentence, you may actually not clearly hear a specific word, but it's the one that makes sense. The next word in the sentence may make sense. If you say a sentence and you know that the next word should be sent, but it wasn't clear enough that just said by itself, you could misinterpret it as bent, sent, tent. Your mind will fill it in as sent. You won't even realize that, okay? So in our tests for clarity at a distance, we actually take isolated words, and the words that rhyme, that could be mistaken for each other. No way of knowing what that word should be because it's not in a sentence. It's not something that gives you a clue as to what it can be. And that's where we listen to a string of words and we rate the clarity of the system. That is a good way to rate the clarity of the system at distance, not with SPL. And that's the conclusion of the presentation.